Here's problem 3626. A contact lens is made of plastic with an index of refraction of 1.5. The lens has an outer radius of curvature of plus 2 centimeters and an inner radius of curvature of 2.5 centimeters. What is the focal length and the power of the lens? Alright, so let's imagine we can construct this lens. The first radius of curvature is 2 centimeters. Let's call it R1. And the second radius of curvature is a little bit less abrupt, and that one is 2.5 centimeters. Let's call it R2. We might have light converging from the left, so that's our light direction, and it's going to encounter this lens. This lens is going to focus. Okay, let's apply the lens maker formula to this lens. We have 1 over the focal length will equal the index of refraction minus 1 times 1 over the radius of curvature of the first surface minus 1 over the radius of curvature of the second surface. So this would be 1.5 minus 1, 1 over 2 centimeters minus 1 over 2.5 centimeters. So this will be 0.5 times 1/2, 0.5, minus 1 over 2.5, which would be 0.4. So we'll have 0.5 times 0.1. So 1 over the focal length will be equal to 0.05. So the focal length will be 1 over 0.05, or 20 centimeters. So we have a focal length which is a positive 20 centimeters, which means we have a converging lens, and the power is defined to be 1 over the focal length. So that's going to be 1 over the focal length in meters, so that's going to be 1 over 0.2, or 5 diopters. That is the power of this lens. It's positive. So that is a converging lens. This might be a lens that might be used for somebody who was farsighted. Most nearsighted people would have a diverging lens to help converge the image onto the retina. And then the power of that would be negative in terms of negative diopters. So the power of this lens, 5 diopters, focal length 20 centimeters.